Hello everyone, welcome to my YouTube channel. In this video, I am going to show you how to convert that non-linear rescue location optimization problem to linear. So if you haven't watched my previous video, please watch that. I have explained the problem and the non-linear solution in that particular video. So in this video, our goal is to convert that non-linear problem to a linear constraint. Okay. So how can we convert that non-linearity? So the reason for that non-linearity is that we had absolute function. Okay. So we need to find that absolute value of those x distance and absolute value of y distance, and that's why it is causing that non-linearity. So how can we do that? And we can remove that absolute condition and then make this to a linear model. Okay. So I have found this documentation, so I'll add that link in the description so you can check that documentation, but I'll just show you the main part of this documentation and I'll explain what we need to do. Okay. So it says that the objective function is of the form that minimum or maximum and a1, x1, a2, x2 and so on. What if there is an absolute value in the objective? So in our case we have that absolute value condition because in our case we are extracting average distance per rescue, but that distance depends on this absolute function, right? And that's why we need to convert this to linear condition, right? So that's why what if there is an absolute value in the objective function? So let's first represent by x and this one by y. So basically it's extracting this absolute x and y. So abs x plus y. So depending on the sign before the absolute function and the objective direction. So the objective direction means that if it's minimization or maximization. Okay. And the sign before the absolute function, that means here what sign we have in this particular section. So in our case we had absolute x plus absolute y. So both are positive, right? And it says that our objective function was minimization, right? So minimization and sign is positive or maximization and sign is negative. So if it's minimization and sign is positive, then what we need to do, we need to consider that what is the way to minimize this, right? So if this one, so absolute of x is always going to be a positive number, right? And if we have a positive sign at the front of this absolute function, that means it's going to add into that objective function. And our objectivity is that we need to minimize that, right? So what can we do to minimize this? So the minimum value for absolute function is 0, right? So that's what we can get if we want to get minimized value, right? Because if we put -5 and if we use absolute function, then we'll get +5, right? So it doesn't make any sense to put a negative number and we'll not get that negative number, right? So we need to reduce it down to a 0, right? So that's why it says in these two situations, absolute x will be as small as possible. So ideally 0. We can use that fact, add one variable x prime and two constraints to the model. So we need to add one variable, that is the x prime, instead of abs x, that will be x prime. So the objective function will change to x prime plus y. Okay, so you can see and replace in the objective abs x with x prime. So x prime plus y, and we need to add two constraints to the model. One is that this x is need to be less than or equals to x prime, and minus of x is going to be less than or equals to x prime. So this is the two condition. So that is all. So how does this work? There are three case to scenario. So if it's x is greater than 0, less than 0 and x equals to 0. So I'm not going to explain all of this. You can read the documentation. I'm just going to show you how to set it up. Okay. So we had the same thing in this non-linear and linear. So we have town name, x coordinate, y coordinate, average rescue per year. We have feasible x coordinate, y coordinate by extracting minimum and maximum. And that's I have discussed in previous video, so please watch that video. So the end goal is to find this x and y coordinate of the shelter. So this is our kind of a decision variable, so x and y. And you can see that we need to find this -x and +x, right? So what we do is that we just get this h4 minus d4, that will give me the first town x distance of the absolute function, right? And what we need to do, we need to minus x distance. So that is basically d4 minus h4. So you can see d4 minus h4. And we are extracting that town x distance and town minus x distance for all of those four towns. And then we get this for the y part, town y distance, town minus y distance. Now, as you know that we need to add one variable for each of the town and we need to add two constraints, right? So that is the x prime. This is for town 1. And these are kind of decision variable now, and we will get this value by adding the constraint. Okay, and then at the end, as you can see, that we get this distance, then we get the total distance, then we get the average distance per rescue, right? So this is our objective function. So if I show you the model, you can see that we need to minimize this L12, that is the minimum, and by changing variable cell, now we can see that the variable cells change from H4I4 to H4I4 plus this X prime and Y prime part, right? So H12 and I15. So that is this H12 and I15. Those are the cells that I need to change. And as I explained, that we need to add 2 more constraints for each of those X prime. So you can see that this is my H12. So if I just see that, okay, what do we have? So this is the H12, and it says that K4 is less than or equals to H12. So if we go into this K4, so that is basically this one, X. So this X is less than or equals to X prime. So that is this condition, that X is less than or equals to X prime, right? So that is this one, X is less than or equals to X prime. Now we have one more constraint for this one. You can see L4 is less than or equals to H12. So that is minus X is less than or equals to X prime. So we have 2 constraints for each of those variable cells. So X prime for town 1, Y prime for town 1. So there will be 8 different variable cell. So there will be 16 different constraint, and you can see all of this constraint here. And then we have this integer constraint that, okay, this need to be an integer value, and that's it. That's how we can change this non-linear constraint to a linear constraint, and now we get this solution by using the simplex LP solver model. So if I just will solve, then it will solve that, and it will say that keep solver solution. And you can see the solution is 619270, and we had the same solution using non-linear model 619270. And that's it for this video. If you are new to my channel, what are you waiting for? Please hit the subscribe button. Have a good day.